técnicas, inclusión de IA y paneles flexibles, organizado por el Instituto Nacional de Tecnología Industrial, ARO y FUJIFILM. A continuación, invitamos al escenario a María Florencia Osa, directora de ARO, y a Pablo González Tahuás, jefe del Departamento de Ensayos No Destructivos del INTI. Les pedimos si pueden acercarse al escenario. Ahora sí, invitamos a Pablo a que nos dé unas palabras de bienvenida.
Ahí está. Bueno, bienvenidos bueno, también a los amigos, a los compañeros, a los colegas, operadores, a las empresas. Nuevamente, este año nos convoca acá para tener otro ámbito también de aprender un poco más por fuera de los cursos tradicionales, ¿sí? De compartir alguna experiencia también y sobre todo de ponernos al tanto de, bueno, lo que está, no digo se está viniendo porque ya está, pero bueno, las nuevas tecnologías, ¿sí? El tema de los paneles de la radiografía digital, sobre todo, ¿no? y de los paneles flexibles en particular, es algo que para nosotros requiere la atención porque, bueno, nos parece que es hacia donde está yendo la cosa, ¿no? Así que, bueno, nosotros estamos interesados, digo, en avanzar en esto. Bueno, como ya lo hemos contado, creemos que tenemos ahí algún desafío de avanzar con las certificaciones características de esta técnica digital. Bueno, tenemos el desafío, quizá el contexto no ayuda mucho, ¿no? Pero bueno, nada. Agradecerles a todos los que se acercaron, ¿sí? a este evento también, ya a esta altura del año, ¿no? Que las cosas a veces empiezan a poner cansadores, pero bueno, nada, nosotros la verdad que es una alegría ser de vuelta del ámbito donde nos encontremos, poder poner la casa a disposición de las empresas, ¿sí? ARO es una empresa con la cual, nada, de vuelta, ¿no? Son como los amigos de la casa, le decimos nosotros, de hace mucho tiempo. ARO nos viene colaborando y nosotros colaborando con ARO, ¿sí? Hemos tenido un aporte muy grande en lo que fue ultrasonido Phase Array de ARO, en el armado de los cursos, en el armado de los bancos de pregunta, de las piezas de examen, para el esquema de certificación. Así que, bueno, siempre es un gusto trabajar con ellos y seguir pensando cosas nuevas. Hoy, más allá del Phase Array, avanzando en la otra técnica que es digital. Así que gracias Florencia por, bueno, acercarse al INTI. Así que bueno, nada, aprovechemos la jornada, ¿sí? Aprovechemos a James para hacerle las preguntas que tengamos, sacarnos las dudas y bueno, bienvenidos a todos, ¿sí? Gracias.
Muchas gracias, Pablo. A continuación escuchamos a María Florencia Osa.
Buenos días a todos. En nombre de ARO estoy aquí para darles la bienvenida y agradecerles la participación. Muchos de ustedes no me conocen. Yo soy directora de ARO, responsable de marketing, comercio exterior y muchas otras cosas como pasan las pymes, que somos un poco todos todoterreno. En primer lugar, quiero agradecerle a Pablo y a Eva y a Hernán y todo el equipo del INTI por prestarnos el lugar, ayudarnos con la organización. Como bien decía Pablo, tenemos muchos años de cooperación, así que gracias. Y muy especialmente quiero darle la bienvenida al equipo de FUJIFILM que hoy nos acompaña, Eddie Massetti, Jim Molinaro, Mike Vendam, que vinieron especialmente a Argentina para acompañarnos en lo que es un poquito el lanzamiento de nuestra relación como empresas. Estoy segura que la mayoría de ustedes nos conocen porque están aquí, de alguna manera recibieron nuestra invitación. Así que o son clientes, o deberían serlo, o están en nuestra lista de email marketing. Bueno, así son las cosas del marketing. O alguno de mis colegas técnicos tiene su contacto en el celular. Bueno, ahí las cosas que les mandan ya no dependen de mí. Cualquier cosa hablan con ellos. pero estamos muy agradecidos que se hayan tomado el tiempo para venir a estar aquí presentes. Les resumo un poquito para los que no nos conocen tanto. ARO es una empresa que se fundó en la década del 60, lo que implica que tenemos más de 60 años de trayectoria en Argentina, siendo líderes en todo lo relacionado con los ensayos, la metrología, el control de calidad. Hemos sido pioneros, incluso con nuestra propia fábrica en algún momento, hasta la crisis del 2001, y seguimos siendo partners de empresas de renombre mundial, que nos acompañan hasta el día de hoy desde nuestros inicios, empresas que en más de 50 años han estado confiando en nosotros, en nuestro equipo, en nuestra trayectoria, en nuestra ética de trabajo. Eso es lo que nosotros creemos es nuestro mayor capital, nuestro equipo de trabajo, que cuenta el día de hoy con gente que ha encontrado en ARO su primer trabajo y hace 50 años que nos acompaña. Se podrán imaginar los días de vacaciones que tienen acumulados. Y gente que acaba de salir de una escuela secundaria técnica y empieza a trabajar con nosotros a aprender. Esa conjunción entre la experiencia de quienes nos acompañan hace mucho tiempo y los que recién empiezan hacen que ARO tenga ese capital humano de quien conoce a fondo las técnicas y quien trae nuevas ideas y nos impulsa siempre a innovar. Y lo que nos hace tener un equipo que da desde el asesoramiento de cualquier proyecto que cualquiera de ustedes pueda tener, hasta la implementación, el comercio exterior con nuestro propio equipo y el servicio postventa, que es algo que no muchos ofrecen. Estamos seguros de que esos son los motivos por los cuales FUJIFILM nos ha elegido para desembarcar en la región y en Argentina, y es un gran orgullo para nosotros. Así que bueno, bienvenidos nuevamente, les agradecemos su presencia y esperamos que la presentación de Jim les sea sumamente útil. Muchas gracias.
Muchas gracias, Florencia. Los invitamos a tomar asiento en la primera fila. Ahora sí damos inicio a la jornada, invitando a James Molinaro, que es especialista en capacitación técnica en los servicios de ensayos no destructivos de FUJIFILM. Posee certificaciones como ASNT nivel 3 en radiografía, líquidos penetrantes y partículas magnetizables. Además posee una certificación NAS 410 nivel 3 en radiografía, tanto en convencional como digital. Con más de 22 años de experiencia en la industria de los ensayos no destructivos. James participa activamente en organizaciones profesionales, incluyendo ASNT y ASTM. Contribuye regularmente en el comité ASTM E07 y en las reuniones del comité de la sección quinta del código ASME. En su puesto actual en FUJIFILM, James dicta capacitaciones para personal que busca certificaciones de nivel 1, 2 y 3 en radiografía digital, radiografía computarizada o directa. Su charla abarca comparación entre radiografía computarizada, radiografía digital y adquisición de datos digitales, resolución espacial, cómo comparar la resolución espacial en pruebas digitales con la sensibilidad en películas tradicionales y cómo abordan la evaluación de la resolución espacial y la sensibilidad, las diferentes normas. Al terminar, abriremos un espacio de preguntas. James.
All right. Thank you very much.
You're welcome.
Hola, buenos días, buenos Aires. That's about the only Spanish I know, so just bear with me, please. Very nice to be here. I do want to thank ARO, the team at ARO, Martin, Franco, and Florencia. Thank you very much for the hospitality that you've shown our team. It's a pleasure to be here. And INTI as well, thank you for allowing me to present today. All right, so we'll get started here on digital radiography in the oil and gas industry. I am curious, in the room, how many people here are still using film radiography? Okay, and how many are using digital, whether it's computed radiography or DR? Okay. Excellent. So, yeah, that's interesting to see. And film has been around for years. We all know that. Film has been reliable. It's the known standard. Excellent resolution. Digital radiography has had a lot of advancements recently. Like we were mentioning earlier, we do have flexible detector panels that we'll talk about that are bendable, that work great for wrapping around pipes or putting into cylinders. This is going to be some of the topics that we're going to discuss this morning. So we're going to do an overview comparisons of the different digital radiography technologies. So CR, DR, bendable detectors as well. And then we'll get into one of the important measurements. One of the most important things with radiography is the resolution, the spatial resolution. If we don't have good spatial resolution, we may not be able to find certain indications or flaws. So we're going to compare the differences between film, CR, and DR on spatial resolutions. And then we will also discuss how the different standards, ASME, ASTM, how they want the spatial resolution measured or the image quality of those different systems measured in digital radiography. And then one of the things we have been working on at FUJIFILM as well is using AI, artificial intelligence. We call it ADR, which is assisted defect recognition. A lot of level 2s get worried when they hear about AI or ADR, and I would too, right? I teach a lot of level 1 and level 2 students that are becoming inspectors, and they're worried about AI, right? Taking my job. Trust me, FUJIFILM, we don't want our AI to make the accept or reject decisions on your product. The AI is going to be there to help you, make you more efficient, to perhaps find an indication that you may have missed, and then you still have to evaluate it. So we still need inspectors. So we're not after anyone's jobs. Just wanted to make that clear. But it's a really good tool to help you make your job easier. Ooh, that's not good. One second. Okay. There we go. Okay. That would not be good. Okay. So we're going to talk about the overview of digital technologies. How many people currently use CR, computed radiography? So just one? Okay. And how many for digital or DR? The flat. Okay, excellent. So we'll talk about the differences between the two. They both have their advantages and disadvantages that we'll talk about. And it really just depends on the application. And then we'll also talk about the bendable digital detectors, which are really new to the industry. They've only been out for a couple years now. So it's CR, computed radiography. If you're trying to go from film to digital, sometimes that's the easier way to transition into digital. So this is a hard cassette for CR that you could stick it right into the scanner to scan the imaging plates. The imaging plates, that's a small one. This is one of the imaging plates. These are very flexible. You don't have to use the hard cassette. You can actually use a vinyl cassette or flexible cassette that you use with film. So these are really nice to be able to replace film. You're basically storing a latent image on this imaging plate, and then when you scan it, it's going to create a digital image. And I'll explain how that works in the next few slides. But that's more of a two-step process, very much like film radiography. After you shoot your film, create your radiograph on the film, the latent image, I have to take that film and run it through a film processor. With CR, I run it through a scanner instead of a film processor. But for film processors, they may take 8 minutes before you get one radiograph to come out. Where with CR, you could scan an imaging plate and have a radiograph to look at in about 1 minute, depending on the resolution that you scan it at. And not only that, it's a faster exposure than film. So one of the benefits of the white imaging plate is it's a really fast exposure, kind of like a fast speed film. So I can pretty much get the same exposure. If I was doing a 1 minute exposure on film, I can get the same exposure on this imaging plate in about 20 seconds, or 1/3 of the time. And all this technology really started in the medical industry first. FUJIFILM, we were one of the first companies to create digital radiography using CR in the medical industry. One of the main reasons that they wanted to go CR in the medical industry is, doctors, they really don't like to x-ray you unless they have to, right? Radiation, not good on the human body. So if they could speed up the process during the x-ray exposure, that's a benefit to the patient. So speeding up the process, the patient is receiving less dose. So the medical industry, they started in the early 80s doing CR. It really didn't get into NDT until the 1990s. There was a lot of pushback in the beginning. The resolution in the beginning with CR wasn't the best. So a lot of level 3s were like, no, we're going to stick with film. But the technology got better. The resolution is much finer now. We can actually scan imaging plates now down to 25 microns, or 1/1000th of an inch, to find really small indications. So it's really come a long ways. But it's a two-step process. We still have to scan the imaging plate. Where digital radiography, or DR, we could capture that image directly onto that detector. This is just a prototype or a mock-up of one of our DDA flexible detectors. This is a new technology to FUJIFILM as well. But it's oil and gas. There's a big need for a detector like this, that we can wrap it around the pipes, have your isotope or collimator up above it, and strap it to it. And you can have an image. You can actually see a live image as soon as x-rays are turned on, or you crank out your source, you will see a live image on your monitor. So you get to see the exposure before you capture it. And then you press the button, it captures it, takes multiple snapshots or frames. These produce really nice, clean images. CR, excellent image quality, actually has better spatial resolution than the DDA. But over time, these detectors, they tend to get scratches, artifacts on them, where with the DDA, you don't see that. So there's advantages and disadvantages to both that we'll talk about. Excuse me, losing my voice. Say both DR and bendable DDA, it's a one-step process. I don't have to pull that and stick it into a scanner or process it. It's going to be done directly on the computer. So there's a lot of advantages of going digital. Recently the cost of silver is really increasing. How much is it now, Mike? In the high 40s for an ounce. So the price of silver keeps going up, and that's one of the main ingredients for film. Right? So it's getting very expensive for companies to purchase film, where a lot of companies are starting to look at digital as a more efficient, cheaper way of doing radiography. So many advantages. So no need to develop the film, or no chemical processing, which is a good thing. When I was starting out as a level 1, that was part of my job, was mixing the chemicals, developer and fixer, and getting it on my clothes and ruining my pants. And it's not fun, right? And there's a lot of maintenance involved with film sometimes. Not only that, but from an environmental standpoint, if you don't have chemistry or chemicals at your building, I know in the United States we have the EPA, Environmental Protection Agency. where if they do find any contamination of developer, fixer, or even the silver of the film into the local sewage or environment, you're talking $1 million fines for your company. So this would be one way to mitigate that risk of having any fines or environmental contaminations. Another advantage too is transmitting your images to a remote location. These are digital files or DCM files, so I can share it with other inspectors, send those images over. Or maybe I'm shooting out in the field and my inspector is in another location, I could send that over to them. Where film, it would have to be hand delivered. Most of my experience has been mostly in the aerospace industry. So what we do when we are inspecting product, we have to make what we call a technique, a procedure on how to shoot a particular part. And many times we need to submit those images to Boeing, Pratt & Whitney, any of the aerospace companies for approval. So when we did that with film, we would have to physically send the film out, wait for them to review it, and then they would send it back, either approving it or not approving it. With digital, I can make a copy of my files and send that to the aerospace company, Boeing or Pratt & Whitney. I could put it on a USB thumb drive and overnight it. You can also, if the files aren't too large, you can send it through email, depending on the size of the file. Quicker inspections, so the process itself is going to be much faster than the film process. I started on film, and so I know it takes a little bit longer to get your radiograph, right? And many times, especially if you're shooting parts with multiple thicknesses, you may need 2, 3, sometimes 4 different speeds of film in one cassette, and you have to process each one, separately, or one right after another. So it might take 8 to 15 minutes by the time you could look at all the radiographs for that one shot. Where with digital, CR and DR, we have more shades of gray, more latitude, more dynamic range, where on this one imaging plate, I could get all those thicknesses all in one exposure, and I'm able to adjust it, which is a really nice advantage. Once film is processed, it is what it is. Hopefully it's a good shot. Hopefully it has good contrast, right? Or it's not over or underexposed. With digital, if you're slightly underexposed or overexposed, you can brighten it up and darken it. You can add contrast to it all through the software, which is a really nice advantage. But yeah, it's going to help speed up your production time. And in cost savings, like we mentioned earlier, the cost of film, it's not getting any cheaper. If you take care of your imaging plates, these are reusable. The nice thing about CR is once we scan the image off of it, it also erases the imaging plate. And then we get to keep reshooting it, which is a really nice thing. They are consumable items. They're not going to last forever. But you should save enough money off of one imaging plate that one imaging plate, you should at least get 500 exposures out of one imaging plate. And if you look at the cost of a box of film, we're probably talking for 100, and these are US prices. So a 14 by 17 box of film, 100 sheets of film, can cost $800. Is that right, Mike? Where the imaging plate, the white one, may cost $700. And remember, that box of film only comes with 100 pieces of film. So once you get through the 100 pieces of film, there's $800 gone. But with that imaging plate, if I take care of it, I've seen companies get over 12,000 exposures. I mean, that's a lot. But we typically say if you get at least 500 out of it, you're saving a lot more money compared to film. And a lot of it is training. Part of my job is to train customers how to handle imaging plates. Usually a lot of the film guys, we have that muscle memory where we're opening our cassette, we grab the corner of the film, slide it out, slide a new one in. With the imaging plate, you don't want to slide it. That can scratch it. You want to make sure you open it up completely and lay the imaging plate in there carefully. The better you take care of it, the longer it's going to last you. But it's going to reduce your cost over time compared to film. And I don't have to buy a developer and fixer. And also storage, archiving. So archiving your film. Some companies have their own warehouse where they store that film, or they send it off to other companies to store that film for them. Which, you know, for film, it could be a large facility that you need to store that film. With digital images, you know, you could store it on a hard drive, on a server. There actually are cloud services today that will store those images as well. So archiving is going to be much easier for you. Less rework or reshoots. Absolutely. So some of you may have made this mistake like I have when I was starting out as a trainee. I had my film in the cabinet, put my part on there, getting ready to press the X-ray on button, and somebody comes over to talk to me. You know, what'd you do over the weekend? What are we going to do this weekend? Or you start talking about football. You get distracted, and then that person walks away 5 minutes later, and you're thinking, did I press the X-ray button or not? I can't remember. Has anyone here ever had that happen? You just kind of lose track. So with film, if I did not press the X-ray on button, and I assumed that I did, I'm going to take that film, run it through the processor, and what's that film going to look like when it goes through? If I didn't press the X-ray button, it's going to look clear, right? There's not going to be any silver left on it. It's all going to come off. So that just cost me $8 for that one piece of film. I wasted time. I wasted money. Where with DR, digital radiography, you'll know when you have an X-ray on because you'll see a live image, and then you can acquire it. With CR, I can make that same mistake where if I don't press the X-ray on button and I don't realize that I didn't do that, and I scan it, the image is going to come out completely blank. But at least with CR, I didn't waste any money as far as film or a consumable item. I just have to reshoot it, and then I keep going. And then sometimes if people are using the wrong energy KV settings, maybe the shot would be a little bit too light or underexposed on film or too dark on film. With digital, we have ways to adjust it. We can adjust the contrast and the brightness of that image, which better image quality. Wider dynamic range, which means more shades of gray in one image. So most of the radiography systems or digital radiography systems today are at least a 12-bit for bit depth, which is 4,096 shades of gray. And then the DDAs and CR systems have 16-bit, where it's 65,536 shades of gray. So a lot more latitude. And I'm going to pull up the software just as a demonstration to sort of show you. So this is FUJIFILM's Dynamics VU software. This is the main window when you first open up the software. So here's an image of a radiograph of a couple of castings. So I can hit View Image. And then there's just our step wedge of IQIs on blocks. Right now I didn't make any adjustments. This is just the way that the image opened up. But with film, you cannot see all of these step wedges or blocks all in one image. Right? With film, you might see these three, those three on a different speed of film, and then the rest on another speed of film. But with digital, we have more latitude, more shades of gray. So we can acquire all those thicknesses in one image. And what's nice, too, is we can make adjustments to the contrast. I can really start to, let's see how that looks. So now I can see my my 2 T-holes. It may be a little bit too bright there, but I did not erase or damage anything in the image. If I lighten it up, now I could see these penetrometers over here on this side. We also have them over there. And there are even ways with the Fuji software that I could adjust it to see all of them at once. It just depends on the settings that you use. This is a 16-bit image, so this has 65,536 shades of gray. With digital radiography, we don't measure film density or optical density anymore. We measure pixel value. So anywhere I move my cursor on the screen, it's going to display my pixel value over there. So the more dose the detector receives, the higher the pixel value is going to be. Just like with film, the more dose film receives, the darker it appears, the higher the optical density is going to be. This is very similar to film in appearance, the way that we have it right here. So this is considered a negative image. There's a lot of new radiographers getting into the NDT industry that don't have any film experience, and they sort of like looking at positive images, where I can invert the shades of gray to make it look positive. And that's adjustable as well. So some people prefer to see it in that mode. Me, I started on film, so I prefer the negative. I try to be a positive guy, but I prefer the negative imaging. Okay. So there's a lot we can do with those imagings. So we'll focus on CR on these set of slides. So the imaging plate, it's a flexible imaging plate, and it's coated with different phosphorus materials. We've got some barium, fluoride, europium are some of the main ingredients on these imaging plates. These imaging plates don't have pixels on them. You know, pixels are a digital representation of your image, but when it scans the imaging plate, it creates pixels off of it. They call this a photo-stimulated imaging plate. The word photo, you know, we hear that word photo in the United States and we think of pictures or photographs. The word photo means light. It comes from the Greek word phos, P-H-O-S. So this imaging plate is photo-stimulated. X-rays. X-rays are a form of light. It's just in a wavelength that's not visible to the human eye. It's a very short wavelength. The shorter the wavelength, the more penetrating power we have, or ionizing power we have. So we are taking short wavelengths of light, or X-rays, or gamma ray, and we're storing that energy into this imaging plate. And then we have to take it over to the scanner. So the scanner has a red laser light. So again, we're using another light that's going to stimulate the imaging plate. So as that imaging plate gets stimulated, it's going to release a bluish light that we call photo-stimulated luminescence, or PSL for short. And that blue light is going to represent the dose that's stored on the imaging plate. The more dose, the brighter the light, the higher the pixel value. Does that make sense? Just in a nutshell, that's how it works. I've got another slide that'll help explain it. And then that raw image is going to be sent over to the computer. The computer has its own processing algorithms to help make the image look better than the raw image. And monitors, display monitors, typically high resolution, very high contrast monitors. A lot of the monitors that we sell at FUJIFILM are actually medical grade monitors. That's what the doctors use for mammography or for regular X-ray in the medical industry. So the strengths of CR is going to be the processing speed. Like I said, scanning an imaging plate only takes a minute for a 14 by 17 at 100 micron scan. If I scan it at 50 microns for higher resolution, it takes about 1 minute and 20 seconds to scan it. And then 25 micron, which is our highest resolution for CR, that would take around 4 minutes to scan and erase the imaging plate. But it's still faster than film processing. Cost effective, so when you are deciding to go digital, CR is one of the more affordable and easier ways to go into digital radiography, depending on your applications, right? So, if you're going from film to digital, you can use the imaging plates very much like you did with film. A lot of your existing techniques, you can use the same angles, geometry, source to detector distance, source to object distance, very much similar. Where DR, you might have to make some changes to your technique. Portability, yeah, so these imaging plates, just like film, I could load them in hard cassettes or vinyl cassettes and carry them out to the job site to do my job. So they're not very heavy. Ultra high resolution. Is anyone here in the aerospace industry, or is it mostly oil and gas? No aerospace? Or aerospace? Okay. So there may be a need for 25 micron scan for some of your applications if you're looking for really small indications. So we have that option, but honestly, most people are fine with 50 microns, especially in oil and gas. IPs are flexible. Again, we could use them with the vinyl cassettes. You can also use LED screens with the imaging plates to cut back on Compton scatter, just like you did with film. With imaging plates, it's not an intensifier. It's strictly just a filter. But it does a really good job of cutting back the scatter. So yeah, suitable for pipeline welds, pressure vessels, and structural components, just like film. So here's a slide just showing you sort of the process for computer radiography. So test object is placed on the imaging plate in a cassette, not directly on the imaging plate. Test object, it's going to be exposed to radiation. So you can see the test object is thicker here, thinner, and then nothing over here on the test object. So this area of the test object, that's going to absorb most of the dose. Most of the photons are going to be attenuated or absorbed in that area. So you can see we don't have as many photons reaching the imaging plate. Over here, it's a thinner thickness there. So we're going to have more photons reaching the imaging plate here. And then on the edge, there's nothing there to absorb the photons. I'm sorry, yeah. So it's going to absorb full dose on the edge, just like with film. Then we put it into the scanner. That red laser light is going to stimulate that imaging plate. The more dose it has from the photons, the more light it's going to release. And we're taking X-ray, which is, again, a wavelength of light, just we're not able to see it. It's converting it into a longer wavelength of light. So that red laser light is stimulating it, and you would see a blue light coming off of the imaging plate. And that's what the scanner needs to see. It's going to read the amount of light coming off of that imaging plate, and it's going to create a pixel value or an optical density for that. So this area is going to release a lot more light, so that's going to have the highest pixel value. Over here, it's a pretty good amount of light coming off of it. Over here, very little, because most of the dose was absorbed by the test object. So this over here would be a high pixel value, medium, and then low, which would appear as a lighter shade of gray on the low pixel value. The high pixel value would appear darker, or sometimes completely black. And then after we are done scanning that imaging plate, it's going to be subjected to a bright white light inside of the scanner that's going to erase it or normalize the imaging plate. And then we get to shoot it over and over again. So that's one of the nice things with the imaging plates is it's reusable, where film is just a one-time exposure. And this is a drawing of what's happening in the scanner. So again, we got a red laser light that's hitting this rotating mirror, and that's going to create a linear red laser light. And that particular wavelength of light is what stimulates the IP. That light is going to go through what we call a light guide. This is not a bucket of water that we're pouring on the imaging plates. It's kind of what that photo looks like. But water is very bad for the imaging plates. It can damage it. This is actually a clear plastic that is going to transfer the light from the imaging plate to the photomultiplier tube, or PMT. The photomultiplier tube is measuring the amount of light coming off of the imaging plate. And then it's sending an electrical signal to the next device, which is our analog to digital converter. So the visible light that is coming off of the imaging plate is analog. It's not digital. It's going to the PMT. We're measuring the light. The signal from the PMT to the ADC is also analog. There's nothing digital about that just yet. It's an analog voltage. And then once it goes through the ADC, it's going to convert it to a pixel value, or a digital shade of gray, and assign a binary code to each and every pixel that makes up your image. And it does it really fast. There's really not much lag here from when the light is transferred. And then the imaging plate is just going to move through at a particular speed. If I do a 100 micron scan, it's going to go through pretty fast. If I do a 50 micron speed, it's going to slow down about half of the speed. And it's taking finer slices of light. 25 microns is going to be even slower. So it's really interesting to see that, how we took a very short wavelength of light, X-ray photons, and created visible light that's a longer wavelength that is visible to the human eye, and then we create a digital radiograph off of that. For computer radiography, FUJIFILM, we have 3 different imaging plates. It just depends on your need and application, which one is going to be best for you. The ST6 was the first imaging plate that we released for industrial radiography. One of the main advantages to the ST6 is the speed. Like I said, I could get the same exposure on that imaging plate that I would on film in about 1/3 of the time. So it's a very fast imaging plate. It would be like your fast speed film. For thicker parts, it's going to absorb that dose a lot quicker. But it's not as sharp as the other 2 imaging plates. So depending on the size flaws that you're looking for, that may or may not be the best imaging plate for you. It just depends on your what you're looking for in your welds. But for most welds, it works just fine. But we've made some improvements to the white imaging plate. We call it the FR3 now. So the main advantage of the FR3 is it's going to be almost as fast as the ST6, but with closer to the resolution of the UR1. So that's really huge for a lot of our customers. Some of our biggest customers, they use the UR1s for a lot of aerospace parts. And some of their exposures might be 2 or 3 minutes long, just for one exposure. And these are companies that are producing hundreds or thousands of castings every day. So if we could speed it up to 30 seconds of an exposure, that's a huge increase in production time. So we've got a lot of customers that are really interested in that FR3. And it's not as sharp as the UR1, but it does meet a lot of the aerospace requirements for image unsharpness, or UG. The UR1, great imaging plate, but again, one of the advantages to that, or disadvantage I should say, is it's a slower imaging plate. And that's the blue one that we have here. This one's slightly thinner, So the phosphor materials on this are smaller, they're finer, better refined on this imaging plate, which gives us better resolution. And it actually is a little more flexible than the other imaging plate. But this is one of the main ones we use in aerospace, especially on thin wall materials. This imaging plate works really well. But like I said, it takes a little bit longer to get the exposure that you need. So I really think this is going to be a good one for Fujifilm, the FR3. It's something new that we just started to release in the United States. And then you can see the picture over there just showing you which one's the fastest, which one has the highest resolution. So I think for most people here, the FR3 and the ST6 is going to be great for the oil and gas industry. And then anyone from aerospace, the UR1 and the FR3 would be the best for those applications. And there are different scan resolutions with our latest scanner. So you could scan at 200 micron, which isn't the best resolution, but it would be a really fast scan. Takes maybe 30 seconds to scan that one imaging plate. But it's very grainy, you know. But for looking for foreign material in a part, it might be better suited for that. 100 micron, that's the first scan resolution that most people use. 50 micron is probably one of the most commonly used in oil and gas and aerospace. 50 micron will help you see flaws down to 0.002 of an inch, or 50 microns. And then 25 micron, which 25 microns not always needed, just depends. I think for oil and gas you really don't need it unless you're looking for really fine indications. So that's computed radiography and how that works. And now we'll talk about DR, digital radiography. So digital radiography actually started in the medical industry, just like with CR as well. The original detectors were rigid, meaning they're not flexible. There's a flat panel. You can't wrap it around the pipe. So a lot of times they were used in automated systems with a C-arm setup where you got an X-ray tube and a detector, and it could scan the part, move to different angles. The part can rotate. Works really well with automation. We also have resolution now that we could shoot parts directly on the detector. For a long time, 200 micron was the best resolution you can get, but now we've got detectors down to 75 microns, 100 microns. The technology just keeps getting better and better. So we're at a point where we can use it with the parts directly on it. One of my favorite things about it is we can also see real-time images. So as soon as X-rays or gamma rays are applied, you could see a live image of what you're about to acquire on your radiograph. So sometimes with film and CR, you don't know if it's a good shot until you process it. With DR, you're going to know if you got the right angle. You could see your penetrometers for image quality before you acquire the image. And then it's basically going to directly send those images to the computer, which we call a workstation computer, and that's the computer that has the software to process that image. And then it's going to be displayed on a high-resolution monitor to evaluate that radiograph. The strengths of DR is it's the fastest processing speed for two-dimensional images. I can have an exposure in about 1/4 of a second. Probably not going to be the best looking image, but typically what we do with DR, digital radiography, something that helps make the image look a lot cleaner, less noise, is frame averaging. Frame averaging is the detector taking multiple snapshots of that one view, and it starts compiling each view together and superimposes it, and that's going to help reduce any electronic noise. So I usually start around 16 frames for average, and if I do a 1,000 second exposure for the frame, it would take about 16 seconds to acquire that image, and that typically is a good looking image at 16 seconds. I can make it faster with less frames, but you might start to degrade your image quality. So it's completely controlled by you as the operator. You get to control how many frames you want to average, what your integration time is. You can control the gain settings on that detector. Sometimes in digital radiography or in the oil and gas industry, most of us are using isotopes. Or if I have a source of iridium-192 that's getting old, maybe has 10 curies left, it's weak, I can increase the gain of the detector to get that image faster, even though I have less photons coming off of the isotope. So it is adjustable, where CR, you really can't adjust the imaging plate. All you can do is scan it at different resolutions. But with DDA or DR, we have much more control over the image quality. High resolution, like I said, a lot of them now some are down to 75 microns, 100 microns. There's other technology, CMOS, complementary metal oxide semiconductors. Those can actually go down to 50 microns, but they can't handle as much energy as these detectors can. So they're kind of limited as well. This is one of our most successful DDA detectors on the bottom right corner. That detector can actually take up to 15 MeV. So you could use linear accelerators with it, cobalt 60. It can handle that much energy. The other ones might be rated at 320 kV. I believe the flexible detector we have here, this one's rated to 350 kV, but that one's a lot cheaper than the one on the bottom right. So it really just depends on your application, which one's going to work best for you. But again, the advantages is processing speed, real-time capability, image quality, or high resolution, excellent image quality. Your images are going to look a lot cleaner than CR with DDA. You don't get scratches or artifacts on a DR image. But, however, they are a consumable item too. They don't last forever. A lot of my students will ask me, well, how long is that detector going to last? And I really can't answer that. It really depends how you are going to treat it and how you're going to use it. So if I'm shooting that with cobalt 60 every day, really high energy, it's not going to last as long as somebody using iridium-192. Or sometimes people drop the detectors, which, that can damage it as well. But if you take care of them, you're still going to save a lot of money compared to what you would do for film. But just be aware of that they are consumable items and do have to be replaced. But I've seen the detector there on the bottom right. We've got customers that have been shooting them for 7 years and have not had any issues with them. So again, it really depends how you treat those detectors. Again, excellent image quality, frame averaging is really going to clean up your image quality. It works great for welds, pipelines, pressure vessels, and structural components. So this was, these pictures here were about 6 weeks ago. I got to test the bendable detector for the first time at one of the labs in South Carolina. So this was a 6-inch pipe that we made. It's actually a pipe phantom, excuse me, that's required by ASME Section 5 of the code. They want you to have a phantom to prove out that your detector is going to have enough sensitivity in it. So we were doing some testing there with iridium-192. It was maybe 20 curies. It wasn't that strong of a source, but we were able to get the images that we needed. Nice thing with the system, it comes with a portable laptop. It's one of those rugged laptops that's designed for outdoors. It is water resistant, so it works great out in the field for pipeline applications. So bendable detector captures images in real time, so even with that detector, we can see a live image before we actually acquire that image. This particular detector can bend down to a 4-inch or 100 millimeter diameter. It could also become larger too, just depends on what you need. Faster processing speed, it's a one-step process. We can have the image acquire instantly. High resolution, so that particular one is 100 microns for spatial resolution. Same thing, frame averaging, just like the rigid detector. Pretty much same technology, just it's bendable. This is actually a protective case for our, we do sell these portable detectors. These are not flexible, these are rigid, but it could be good for corrosion shots or for checking valves. Those work really well for that. This is a protective cover for those detectors to help them last longer. You don't want to put the detector directly on your product because it could scratch the face of the detector. The detector goes inside of this and it's well protected. Let's talk a little bit how digital detectors work, just like I did with CR. So over here, this drawing, this is an example of a amorphous silicone detector. So all these little squares that you see, is that me? Oh, losing reception. Okay, no worries, thank you. So each of those little squares that you see, those are actually the pixels that are going to make up your image. And what we have to do, just like we did with CR, we have to take short wavelength X-ray photons and convert them into longer wavelength that becomes visible. Those little pixels or sensors, they're very much like a camera sensor. Camera sensors can only see visible light just like the human eye can see. So we have to take these short X-ray photons and this material that's on top of the pixels is going to convert it into a longer wavelength. We call that a scintillator. Cesium iodide is one of the scintillators that they use. Others are gadolinium oxides. So all they do is turn X-ray into visible light. So if you opened up your detector and turned the X-ray on, you would see that glow. So that glow is going to be adjusted by how much dose that scintillator is receiving. The more dose, the more light is going to come off of that scintillator. And then the little photodiodes or pixels measure the amount of light coming off of that scintillator. The more dose, the more light, the higher the voltage. And then it sends the electrical signals out to the amplifier, multiplexers, and address drivers. So each and every pixel in your image has an address, X and Y address. And then it's going to be assigned through the address drivers. Those analog signals have to go through the analog to digital converter, or the ADC. And then it converts each pixel into a shade of gray or a pixel value. Something to look at when you are shopping for detectors is the pixel pitch. Pixel pitch is measured from the center of one pixel to the center of an adjacent pixel. And that's going to give you an idea of how small of an indication that detector might be capable of getting. So, like I said, for a while, 200 micron was the best you can get, maybe 10 years ago. But now the technology has gotten better where we have 100 micron pixel pitches. So that could be down to 4,000ths of an inch for in inches. 75 micron would be around 3,000ths of an inch. So the finer the pixel pitch, the better your resolution is going to be. Excuse me. So this is really up to the level 3. They need to know what are the smallest size flaws that we're looking for. I don't want to buy a detector that's not going to be able to find the smallest flaws that we're looking for. So resolution is really important, something to consider when you're designing to go digital. Another technology that's out there, this is less common in non-destructive testing, is the direct conversion. Instead of amorphous silicone, we're using amorphous selenium. It's going to do something similar. It's not going to change the wavelength of the X-ray photon. It's measuring the dose electrically. So it's directly converting that dose into a pixel value. So you can see the photons coming through on the amorphous selenium layer, and it's creating an electrical charge on top of one of the pixels, just like it is over here. The more dose, the more of an electrical charge we're getting off of that detector. And then you can see some electrical transistors that we call TFT arrays. A transistor is like a switch in an electrical circuit, very much like a shutter button on a camera, if you think of it that way. So you can see right now we have potential energy right at that transistor. The computer is going to tell it when to acquire. And when it acquires, that transistor is going to be triggered. The electricity is going to flow down to the multiplexer. Again, more dose, the higher the voltage. And then it is going to go through the ADC and become a digital image. One of the advantages to a direct detector is they're very sharp. So if it's 100 micron pixel pitch, your spatial resolution typically is right at 100 microns. So they're very sharp. So it produces, on this, you can see all these pixels that are darkened by the amount of photons. There's no noise or bleed over on the other pixels around it. But one of the disadvantages of a direct detector is they can't handle as much energy. So they're typically not used in NDT as much as the amorphous selenium detectors. Could be more for medical industry. But indirect, that's what this type of detector is. It uses an indirect method. These are most common in NDT. So again, we have to use a scintillator. So you can see the same 5 photons coming through the test object, which are creating light. So that cesium iodide scintillator, the more dose it receives, the brighter the light is going to get. But one of the disadvantages of light is it likes to travel in all directions, right? So because of that, you might have a little bit of blurriness. It may not be as sharp as the direct detector. So you can see the result over there from direct to indirect. But it's pretty negligible. You might lose 8 to 10 microns of sharpness. Really not much at all. But you can see how it affected the image over there. But the rest of it operates the same way. The voltage is going to go to the TFT array, and then when it's triggered, the voltage is going to go through the ADC to create a pixel value or shade of gray. So I know I've been saying a lot about digital and talking about film. I'm not saying that digital is just better than film. Film still has advantages too. Right, Mike? Mike is our film specialist at FUJIFILM. So he knows more about film if you guys have any questions. But it's still a great process, you know, but it is becoming more and more expensive. Right, so the advantages of film is it has higher spatial resolution than even digital at the moment. So film is still king when it comes to spatial resolution. So we could achieve up to 20 line pairs per millimeter. It's widely understood, right? Everyone here is pretty much using film. We've been using it for years. It's a known standard. Very flexible. And we could also cut it into special shapes if we needed. And available in different speeds, depending on your application. But the disadvantages would be a longer processing time. We have to use chemistry to create the radiograph. And with the silver prices increasing, it's becoming a very expensive way to do radiography. Something that I've noticed too is even though film has excellent spatial resolution, I feel that digital has better contrast sensitivity. And what good is that spatial resolution if you don't have good contrast in your image, right? I've seen indications missed on film that we found on DDA or DR. And we kept shooting it on film and DR, and we can never find this really small porosity. Just the film didn't have the contrast sensitivity that digital had. Digital is so sensitive that you can even see the tape. If you put an IQI and you tape it on a part, you can see the tape in your radiograph. Where with film, you don't see that. It only has so many shades of gray to it. And darkroom, you need a darkroom to process the film. With CR, I don't need a darkroom, especially if I use the hard cassette. If I'm using vinyl cassettes, though, you do want to be careful. You don't want the phosphors exposed to overhead light. It can start to erase that imaging plate. So many times people keep it face down when they put it into the scanner. Or just leave it in the hard cassette and it never sees any light. So you don't need a dark room like we do with film. And it has low dynamic range and latitude, so not as many shades of gray that we have like with digital. And plus we also need space to store all that film as well. Here's advantages, disadvantages of CR. So that on the top right of the image, the HR square or HR2, that's our latest CR scanner. And then the one to the left, that's one of our older scanners, the HR, but it was a really good system. That's the one that I started with FUJIFILM. But you can see it's talking about the process up there in the middle slide or middle picture. You got a blank imaging plate. We're creating a latent image with X-ray or gamma ray and scanning the imaging plate. And then it's going to erase it, and you just keep using it over and over. So at CR, 25 micron, 50 microns, we can get high spatial resolution down to about 10 line pairs per millimeter, faster processing time. The IPs are reusable, flexible, and portable. And then also digital image processing. There's a lot we could do with that digital image to enhance it. We could sharpen it. We can use edge detection. And what else? Yeah, you can also cut your imaging plates to special shapes. So if you have a corner with an angle that you got to get into, I can't put a square into a corner like that, so you could cut that into an angle. Is that me? Okay. Easier archiving your images. So like I said, you can store it all on a hard drive, on a server, external hard drives, however you want to store your images. Superior latitude compared to film. So yeah, they could be a 12-bit, 14 or 16-bit system, which means more shades of gray, more latitude, less double loads or triple loads of film. Environmentally friendly, no darkroom needed. We do have some customers that have that scanner in the back of a truck that they drive out to a pipeline field or refinery and process it in the back of a truck. Higher contrast sensitivity than film, absolutely. Like I said, I've seen indications on CR that were not visible on film, which in the beginning, probably like you guys, I started on film. I didn't really trust digital in the beginning until I started to use it and see its capabilities. And now I am spoiled. I don't want to go back to film. So, not that it's a bad thing. I just prefer digital. Disadvantage for CR, so it's going to take longer to get your radiograph compared to DR, digital radiography. Lower spatial resolution than film. So film still has better resolution than CR. And then over time, you are going to start to get scratches on your imaging plates. You might get dust or debris. Sometimes your lead screens, they start to oxidize over time, and those oxides can get into your imaging plate and show up as indications. So if those indications or artifacts start to get too big that you think it could be masking a rejectable indication, it's probably time to get a new one or shoot a different imaging plate. And over time, too, the image plate sensitivity will start to degrade. So the pixel values are, a measurement of dose on the imaging plate. If I'm shooting that imaging plate and I've got over 2,000 exposures, most likely the radiation has started to degrade some of the phosphors in the imaging plate, and it might not give off as much light, and your pixel values will start to get lower. So that's just something to pay attention to. But typically, people are replacing those more for scratches and artifacts before that starts to happen. And it's a two-step process, just like film. Compared to DR, well, here's comparisons of DR compared to CR. So that's one of the detectors that we sell in the middle. And we are in the development right now of creating an automated DDA system that it will allow the operator to put the part on a turntable, and once the program is set, that system is going to take all the shots automatically. A lot of companies are really liking automation just for production, but oil and gas, not going to be using automation as much, right? You're not in a cabinet like that. You're out there in the field. So like I said, we do have portable detectors for the field. High spatial resolution, up to 5 to 7 line pairs per millimeter. Nice thing about it, too, is immediate image acquisition. Again, depending on what my settings are, I can have an image to evaluate in 1/4 of a second. And frame averaging, again, that's a really good quality of DR, is multiple frames can help clean up your image quality. Digital image processing, just like we did with CR. So we could adjust contrast, brightness, sharpening, edge enhancements, turning it from a negative to a positive image. And DDA or DR adapts well to automation, much better than CR. CR is a two-step process, so it's much harder to automate that. Where DR, I could leave my detector in that cabinet and I don't have to pull it out. It's going to instantly give me the images without scanning it. Most DDA or DR detectors are 16-bit, so again, that's 65,536 shades of gray that we get to work with. Does anybody know how many shades of gray the human eye is capable of seeing? It's not many. Even though we have 65,536 shades of gray to work with, the human eye may only see 100 to 150 shades of gray. And a lot of my students will ask, well, why do we need 65,000 shades of gray if the human eye can only see that much? The best answer to that is for the data. Even though we might not be able to see all those shades of gray at once, we're able to adjust the contrast in the image. As you increase contrast, that's removing shades of gray from that image, which makes it more visible to the human eye. So the nice thing about having that many shades of gray is to store all that data, and then the computer is able to adjust it best for our eyes to see it. Again, environmentally friendly, no darkroom needed, high contrast sensitivity compared to film. You know, I'll tell you guys a story that I used to work for an inspection company that our customer wanted us to go to an automated DDA system. And it was for electron beam welds. These electron beam welds we were shooting on film for 20 years and really didn't find a lot of rejectable indications with film. This was a very critical part. It wasn't allowed to have any flaws in it, but when we went to the DDA, we actually started finding small micro porosity in the EB weld. And we started rejecting it because we were finding indications. The acceptance criteria didn't allow any flaws in there. So we rejected it, sent it back to the customer, and the customer is like, why are these getting rejected all of a sudden? He's like, we've been shooting them on film for 20 years. we had a really good pass rate, acceptance rate. But now when we went to DDA, we started to find these little indications in there. And they actually asked us if we could dumb down or blur the image to where we couldn't see that indication. It's like, well, why are you asking us to inspect this weld if you don't want us to find anything? So my point is, even though film has the better spatial resolution, the digital system had better contrast that we were able to see these little porosity indications. And I said, can you make your welds better? I'm not going to blur or dumb down my system. So the funny thing is, the way that customer handled it was, if we shot it on digital and rejected it, we would send it back, and then they would send it back to us with another purchase order, and on the purchase order it would say for us to shoot it on film. So this part that was rejected on DR, we were now looking at on film, and we didn't see the indication, so we were able to accept it. I didn't feel good about it. I told them, the engineers, like, the flaw is still in there. The film didn't erase it. We're just not detecting it. So we were covered, and the engineer's mentality was, well, we've been using these, we've been shooting these on film for 20 years, no failures, so they're good with that standard. But anyway, I thought it was an interesting story to compare contrast and resolution. So disadvantages to DR, especially for an automated DR system, the initial cost can be very expensive for that system. Some of the automated systems can run $500,000 to $1 million in US dollars. I don't know what that would be converted over. But very expensive for automated. Like I said, now we can sell detectors where you can shoot directly on your pipe. You don't need automation anymore. The price is comparable without automation, comparable to CR. But even your detector, again, it's a consumable item. So, if your inspectors are out there and they're dropping the detector or scratching it, it's going to get damaged. If you're hitting it with really high energies, over time it's going to degrade. But you're still going to save money compared to film. I just want you to be aware that they are consumable. They're not going to last forever. Lower spatial resolution than film and CR. So at the moment, yeah, CR is better for spatial resolution. But who knows, in 5 years, this might be better than CR for spatial resolution. But it still is enough resolution to meet ASTM, ASME requirements. Most of the detectors are not bendable, so that's a rare detector that we have. It's pretty new, but the one that you see up there is not flexible. And limited field of view. So with our imaging plates, we actually sell some imaging plates that are 3 feet, 4 feet long. If you want to wrap it around the pipe and do a panoramic exposure, where DDA you're kind of limited to certain sizes. We sell a 14 by 17 portable detector. I'm sorry, in inches. That would be, what would that be in metric? 14 by 17. 35 by 43 centimeters. And then 10 by 12 would be, I'm sorry, put you on the spot. 24 by 30. 24 by 30. And we're adding more and more to our lineup as well. And something that does happen with detectors over time, you might have some pixels that go bad. They're just not responding anymore, or they could be over-responding, under-responding. For the most part, the software is able to correct for those bad pixels, but eventually over time, it may grow into a cluster of bad pixels that are not correctable. So that's something that a level 3 would have to decide, is this cluster of bad pixels large enough that it could be masking an indication? Am I missing anything in the image? If I am, you can send them out to get repaired or just replace it. Sometimes because with DDA, it doesn't have as high of resolution as CR, as computer or as film. Sometimes they use geometric magnification to increase the resolution of the image. Are you guys familiar with geometric magnification, what that means? Where, let me show you an example. You pretend my light is my X-ray tube. This is my X-ray photons. So I don't know if that's going to make a shadow. So if we pretend that this is film, and this is my X-ray source, that's not a good example. But basically, the closer I get my hand to the X-ray source, the larger it's going to appear in the image. Maybe I could do it on this wall. So you can see the shadow of my hand pretty close to real size. As I bring it closer to the light source, or the X-ray tube, it starts to increase the size of it, which would also increase the size of any flaws that are in that part, make it easier to see. So that's something that they use a lot in automated systems, is geometric magnification, which is going to give me higher resolution in the image. But you do have to be careful. You can only do this with certain X-ray tubes, like a micro focus or a mini focus X-ray tube. Conventional X-ray tubes, if you start to pull your part off of the film, it starts to get really blurry, right? Your UG becomes too large, or geometric unsharpness. But with a micro focus or mini focus, you can enlarge it, and it's still going to be sharp enough to see what you need to see. But that's rarely done in the oil and gas industry. You're typically shooting directly on the film, no geometric magnification. But that's an option if needed. So here's some slides I put together to explain basic spatial resolution. Has anyone here ever seen that gauge that we have on the screen? They call that a duplex wire gauge or a line pair gauge. And it's a gauge that we use to measure for resolution. And we measure it in the metric system. So our software does have the function where we can draw a line across that duplex wire gauge, and it will automatically measure the spatial resolution for you. So you can see on the top right where it's saying ISRB, 0.046 millimeters or 46 microns is what we measured there. So each pair of wire has a space in between it. The space in between the wires is the same diameter as one wire. So they get smaller and smaller as you go, so the space in between gets smaller. So this is going to help you find the limit for your digital system. But this is really interesting. What I did was took examples of the white imaging plate, the ST6, scanned at 100 microns. We achieved 146 microns for spatial resolution. And then I took the blue imaging plate, the UR1, and I scanned it at 25 microns and got 46 microns as the actual spatial resolution. So even though I scanned it at 100 micron, I didn't get 100 micron for spatial resolution. And that's normal. You're going to see that with every CR system. Remember, light, anytime light is glowing, it's traveling in different directions. So you're going to lose a little bit of sharpness because of that. And this gauge is going to help you understand how much resolution you have in that image, or calculate it. Even though I scanned it at 25 microns, I got 46 for the actual resolution. So be aware of that. With CR and DR, there's always going to be a slightly blurrier resolution than what your pixel pitch is. But here's a radiographic image, digital, of a 100 micron scan with the white imaging plate. So you can see the wires are starting to alias. They're starting to come together instead of be two separate wires. That's because 100 microns not the highest resolution, right? That's considered standard resolution. So we started to lose it around wire number 9. The resolution started to close the wires up. So if I look at the UR1, scanned at 25 micron, Well, this is wire 9. There's wire 13 on the ST6, which looks like one wire instead of two. With the UR1 scanned at 25 micron, well, here's wire number 13 clearly separated. So now you can see much more. Yeah, it looks like two wires instead of one. So that's better than 50 microns. And then even at 40 micron, you can see there is still some separation in there. So that's really high resolution. Not everyone needs it, but it's nice to have it if you do need it. But the main reason I put this slide together, I wanted to show you what film looks like with that same gauge. So I took a slow speed film, class 1 film, and put that duplex wire gauge on it. It took me a while to get a good picture of this, but watch what film looks like for spatial resolution. So there's wire 13, wire 14, and 15. All of them are clearly separated. So just to give film a little credit, how much spatial resolution film still has, it's still better than digital. But we could use geometric magnification, like I showed you on the wall, to get that kind of result with digital. But again, I need a mini or a micro focus X-ray tube to do that. There's two different ways to, or two different measurements for basic spatial resolution, which is SRB, basic spatial resolution. There's SRB detector. That's your duplex wire gauge directly on your imaging plate or on your detector. So that's one of the first measurements you would do when you're getting ready to qualify a system. SRB image, you could put that duplex wire gauge on a pipe or whatever part you're about to shoot and see what the resolution is on top of that part. And that's called SRB image. And that's typically one of the measurements that we need to get when we're making a technique in aerospace. That's one of those calculations that's going to tell us what our total image on sharpness is. So SRB detector, there is no geometric magnification. It's directly on the detector. SRB image is, there is some geometric magnification just by the wire gauge being lifted up off of that detector. And we want to know, well, how blurry is it up at that source to object distance? This is a recommendation from ASTM E2736. If you're looking to go with DR, this is a really good ASTM standard to get a copy of. It's a guide. It gives you a lot of information about DDA detectors, how they work, things to look for, and this is one of the recommendations that came out of that standard. So what they're saying here is the effective number of pixels covering the longest dimension. So one of the things when our salesmen are going to a new customer, I always tell them to ask that customer, what's the smallest indication that your customer is looking for? Because that's really important. I don't want to choose the wrong detector if they're looking for really small indications. So if I only have 1 pixel covering the longest dimension of a flaw, a 100 micron detector, the pixel size is about 100 microns or 4/1000ths of an inch. So if I have flaws that I'm looking for that are smaller than 4/1000ths of an inch or 100 microns, only having 1 pixel cover that indication is not a good situation. It's high risk, right? And a lot of things we have to determine in radiography or NDT is that indication rounded? Is that indication linear? Well, if it's only 1 pixel, that's a square, right? It's not rounded, it's not linear, so I can't really interpret that. If I have 2 to 3 pixels covering the longest dimension, that's better. You still have a little bit of a risk there. 4 to 6 pixels, much better, low risk, but they recommend at least 6 pixels or more covering the longest dimension. So that's something you should think about when you're looking at, should I go with DR or CR? CR, we have 25 micron pixels there, so we can get much more pixel coverage compared to DDA. You know, if you can't achieve the pixel coverage you want, you can always use geometric magnification, but again, you need a mini or a micro focus to do that. This sort of came out of an aerospace requirement, but the ASTM standards adopted it. So, most of us here have used the whole type penetrometers or IQIs, looking for 2-2T. So if 2T is your essential hole that you're looking for, what they want to ensure is, do I have a 3x3 pixel matrix in that 2T hole? If I don't have enough resolution, maybe I would only have a 2x2 pixel matrix in that hole. And that's not good. That's not enough resolution. So like I said, one of the first things you're going to do with your system would be to measure SRB detector. And once you've got your SRB detector measurement, you can use this equation or this formula. So 4.25 times your SRB detector divided by the size of your 2T hole. That would help you determine, does this detector have enough resolution? Or do I need to go with CR, use 50 microns or 25 microns? So just be aware of it. It's not a requirement for ASTM, it's a recommendation. Or no, I'm sorry, this is a requirement. This was the recommendation. So here, if I use the 200 micron detector and I do the math on that, I know that, sorry, that's in inches, but it's telling me I need to use at least 1.74 geometric magnification. And maybe I don't have a mini focus or micro focus X-ray tube, so I can't use that detector. But if I go with a 100 micron pixel pitch detector, and my SRB detector was 110 microns, well, 0.91 means I don't need any geometric magnification. So with these 100 micron detectors now, we are able to shoot directly on it without geometric magnification. And again, pixel coverage, so if I only have 3 pixels covering the longest dimension of the crack, it almost doesn't even look like a crack. So I don't have good definition the way it is on the left side. And that rounded, or that linear indication there, doesn't even look linear. It looks rounded. But if I go from 1x to 2x geometric magnification, well, now it's enlarging the appearance of the indication, just like my hand in the shadow. But now I've got better definition. I can tell that that's a crack, and the other indication on the bottom is linear. But that's using geomag. Well, maybe, if I'm scanning my imaging plate at 100 micron, it's still not the best resolution there. But if I go 50 micron, those pixels are about half the size of one of these pixels, which gives me better spatial resolution. These are some of the image on sharpness requirements by ASTM. ASME, Section 5, the code doesn't require you to do this measurement, but for ASTM, this is something you would measure. But it's something that you would get off of your SRB image measurement. So with that duplex wire gauge, I can measure it and determine what my spatial resolution is on the image, and just multiply that number by 2. So 0.046 millimeters times 2 would be 0.092 millimeters for unsharpness. And then this is a table that came out of the ASTM. So if my material thickness is less than a ½ inch, my unsharpness can't be any greater than 0.010 of an inch or 0.254 millimeters. So this is something to pay attention to, especially in aerospace. Make sure you have a sharp enough image. But again, ASME, the code doesn't require this. They handle it a little bit differently. Sometimes, when we're looking at an image, sometimes our eyes can't really tell us if the image is getting better. If I'm trying to make my technique look better, sometimes I can't trust my eyes all the time. So we do have tools in the software that can measure CNR, which is contrast to noise ratio. Again, contrast, very good. We need high contrast. Noise is bad. Right? Noise can be from scatter, or it could be from the electronics of the system. So the less noise, the higher the contrast, the better the image quality. So you can see the CNR ratio is 0.7 You could barely see the T-hole there. At 3.5, it's much more clear. I could see the hole much better. And then signal to noise ratio. So the higher the signal to noise ratio, or SNR, the better your image quality is going to be. So that signal is really related to your pixel value, or the dose. The more dose that imaging plate receives, the higher the signal. Noise, again, that could be from scatter, it could be from the electronics, but there are ways to reduce that. I do teach that in my level 2 classes, how to reduce the noise, increase your signal. But at the end of the day, tracking your SNR and CNR can help you understand if you're making the image better or worse. And sometimes our eyes play tricks on us. Looking at the software, it's going to be more repeatable and robust. There are some standards that require at least a minimum CNR of 2.5 or greater. Boeing, the aerospace company, did a lot of studies with digital radiography, and the study that they came up with decided if they didn't have a CNR of 2.5 or greater, their probability of detection wasn't that good. So you could miss indications if your CNR is too low. Same thing for SNR. Typically 130 or greater is going to give you better image quality. So DDA or DR is the only one that requires those to be met. CR, you don't have to achieve those numbers, but I still use those numbers when I'm making a CR technique. You know, if I could achieve that on CR, it's going to look really good. So most people here work to ASME, boiler pressure vessel code. So this is what they require for image quality. So they want you to, and this came out of Mandatory Appendix 8, Supplement A. They want you to have a demonstration block to prove out your digital system. And this is really all you need to qualify your system for ASME. So the intention here is to have 2 demonstration blocks. One is going to represent the thinnest material that you work with, and it should be radiographically similar to what you're shooting. So if I'm shooting carbon steel, I want to make sure I have a carbon steel block or stainless steel, whatever your application is. So you want to have the thinnest material and the thickest material that you're shooting. And all they require is the demonstration block has to have a 2% notch of thickness notched out of it. It could be an EDM notch or machined out of it. A wire IQI and a black IQI. As long as you could see the notch and the 2 T-hole on the minimum and the maximum thickness, you're good to go. The system is qualified. You can start running production out in the field. So a lot of guys will shoot this out there in the field before they start the job, just to make sure the system is repeatable, there hasn't been any degradation in it. For bendable detectors, this is the phantom that they want you to have for bendable detectors to prove out sensitivity. So what it is you have 3 notches that are machined out at 2% of the thickness. So those have to be visible in the radiograph. And you can put your wire IQIs or hole type IQIs on there. You don't need 2 different thicknesses for this. All it says in the code is to use the smallest diameter pipe. So that's a 4-inch diameter detector. So I would make a phantom down to a 4-inch diameter. There are companies out there, Flawtech is one that we use in the United States, that they actually made the phantom for me. I just sent them the drawing, and they were able to put the notches in there, and then we just used our IQIs on it. So that was the phantom there that we were testing with the panel. And we were able to achieve the image quality that ASME required with that phantom. So just basics, some things to remember. You know, this kind of goes back to level 1 training. But with digital radiography, guys, you're going to notice that it is more sensitive to scatter than film was. So understanding how your energy or KV can affect your image quality is really important. So KV, the way this slide works is if my KV is going up, my X-ray photon wavelength is decreasing. It's becoming a shorter wavelength, which makes it more penetrating. So the higher the KV, the more penetrating power, the thicker the materials we can shoot through. But KV and contrast are always going to be inversely proportional. If my KV is going up, my contrast is going to start to go down. I've seen some people shooting with film asking me, they were shooting, what was it, maybe 10 millimeters of stainless steel at 400 kV. And they were wondering why they couldn't see the 2T hole on the penetrometer. Really, that thickness, 10 millimeters of stainless steel, maybe 180, 200 kV is what you need to get through it. They were using way too much kV. It was double what they needed, so we could not see the penetrometer. They decreased the contrast of the radiograph that much by using too much kV. And they were just struggling. So also, the more kV, the more Compton scatter, the more scatter I'm going to get from the material. So pay attention to that, because I've seen people going from film to CR or even DR using the kV levels they were using with film and not able to see the 2T hole. And usually my first go-to for them is tell them to lower the kV to increase the contrast. If the image starts to get too light, you can make up for that with your MA for X-ray tubes or your dose or exposure time. So I've noticed that a lot, especially with the blue imaging plate. A lot of times I lower the KV and increase my MA or exposure time, and that is really where you start to see the image get better. So just keep that in mind. Lower the KV, the higher the contrast, and then again, contrast and latitude are also inversely proportional to each other, radiographically and digitally. And I got that note down there. Use just enough KV to penetrate through the material, right? You don't want to use too much. And this is just a table that I put together depending on the thicknesses that you're shooting. So again, 10 millimeters, that customer was shooting it at 400 kV. So it was steel. So here steel at 10 millimeters should only be using about 175, 180. But they were up here on KV, and they could not see the 2T hole. And it was just creating a lot of noise and scatter. So it's like, no, reduce that KV, and then we were able to see it. But that's a really good slide just to get you in the ballpark on the X-ray KV levels you need. So aluminum, very low density, doesn't take much KV to get through that compared to steel and copper. I always try to teach my level 1 students this, and if they understand it and they keep that in their heads, it's going to make them really good radiographers in the future, just understanding the fundamentals of radiography. So here's an example of latitude compared to more contrast. So latitude, we can see more shades of gray, multiple thicknesses, but if I use too high of a KV, you can see that over here I have a 2-to-1 ratio of photons reaching the detector. But if I lower the KV, make that wavelength longer, it's less penetrating power. So here I've got 8 photons, and then here just two photons on the same material thickness. That's going to create better contrast in the image. And then image processing. So over here on the left, this would be a raw image. So this is what the scanner is scanning off of the imaging plate. It's what the detector is reading from the detector. And it looks very blurry, not very sharp. It's very flat. So the image processing of the computer or the VU software from Fuji can enhance that raw image. All the other manufacturers are required to have the same type of processing. So there you can see on the right side the 2T hole, even the 1T hole is really visible, but in the raw image, really not seeing much there. So But you do have to be careful with image processing or filters. This is a good looking image here, the raw, and then when we put some edge enhancement and sharpening, it got even better, much more visible. So it can help suppress noise, enhances edge detection, and can also reassign pixel values. But if you use too much, you can take an image like that and make it look really bad. This is what we consider morphing a digital image. The good thing, though, is even though you may have processed it to look that way, you always have the raw image. So you can undo any of the settings that you put in there. It's usually the level 3 that has to evaluate the image processing that's going to be used for production. You don't want to use too much. Sometimes less is more. So in summary, computed radiography and digital radiography are great techniques to replace film, but you will need additional training if you're going from film to digital. We do offer that in the United States. I do a lot of the level 1, level 2, and level 3 transition classes for people going from film to digital. For NES 410, for aerospace people, S&T, TC1A, CP189, we cover all the subject matter or course outlines that are required by that. What else? So you can see also that CR has its advantages for resolution, right? Digital radiography has its advantages too for speed, production. But you would just have to choose what's going to work best for your application. And then again, looking at your SNR, CNR values as you're trying to improve image quality. Those are good things to look at to see if you're making it better. In the classes that I teach, we really get into more detail on how to improve image quality. And one thing that we do at FUJIFILM too, if you purchase a detector or CR system, we send either the salesman or myself to work with you for 2 days to give you 16 hours of equipment training to get you familiar with the equipment, how to operate it, which would be sufficient for your certification requirements by ASME or ASTM. They require, or S&T, TC1A requires 16 hours of equipment training, so we can help you with that. And again, with image processing, be careful which digital filters you're going to be using to adjust your image quality. You don't want to use too much to where it looks like the image on the right. So here's my contact information if anybody wants to reach out for any training needs that you might have, or if you want to get a hold of me to get a hold of any of our sales guys. And I'm putting a new schedule together for 2026, which will be listed on the website at the bottom.
Thank you very much, James.
Thank you.
Ahora abrimos.
Thank you. Should I ask any questions? Or,
Yes.
okay.
Ahora abrimos el panel de las preguntas. No sé si alguien tiene alguna pregunta.
Sí, gracias James por la charla. Una cosita, primero, recuerden que el certificado justo hablaba de las certificaciones, recuerden que el certificado de esta charla de alguna manera va a servir para las renovaciones, ¿sí? Bajo la nueva norma 2025 de la ISO 9712. ¿Sí? También un poco es lo que hacemos, estas actividades las vamos a hacer para eso. ¿Sí? Acuérdense que las renovaciones ahora van a exigir de alguna manera un sistema de créditos, ¿está bien? Que demuestren actualización y un poco esto sirve para eso. ¿Sí? Eso no lo habíamos dicho, así que estén atentos a los certificados. Y la consulta que tengo para hacer es si puede explicar un poco más el uso de pantallas intensificadoras en el sistema de computarizado. ¿Sí? ¿Quedó?
Oh, there's a delay. I'm sorry, the intensifying screens?
Sí, las pantallas intensificadoras de plomo, por ejemplo. Si se utilizan, si se recomiendan.
Yes, so with the LED screens, let me pull that. So there are certain kV levels where they recommend to use the LED screens, especially with CR. So usually once you get up to over 100 kV, 150, we typically start to recommend using a front screen, maybe 5,000th front screen, 10,000th back screen, just like you would with film. But keep in mind with CR, those screens, they don't act as intensifiers like they do with film. With film, there's an interaction between the electrons of the LED and the film that helps darken that film faster. With CR, it doesn't intensify, but it does filter. So no intensification, but it does have filtration to reduce scatter. So there's just, the ASTM standards do have a recommended energy level where you start to use the LED screens. And then a lot of it can also be experimentation on your own. You know, what do you feel is starting to clean up your image quality? Even though the ASTM recommends 5,000s, maybe try 1,000s, you know, thinner LED screens. But there are certain ones where they just recommend. It's not a requirement or a shall. It's more of a, you should use this amount of LED. Did that help answer your question?
¿Cuál sería la vida útil de los paneles, de los detectores flexibles en términos de dosis absorbida?
How much of a dose?
Yes. The maximum dose.
Maximum dose?
Yes.
So again, that really depends on how you operate the panel. I've seen, we've got detectors that are rigid that have gotten over 7 years of use with no degradation. The bendable detectors do have a certain amount of bends that it can take at a certain number. I don't know those numbers. Have they given that to us yet? How many? 4-inch pipe, but how many bends can we get out of it? Don't quote me on this. For that panel, it's a prototype, but I think I was told 15,000 bends, because what can happen to the scintillator in that detector over time is you bend it all the time, it could start to wear it out. So I don't know a particular number to tell you on that, but that's a good question because eventually it will degrade over time. The more you bend it, the more it's going to degrade. The tighter the bend, the more it's going to degrade too.
No, la pregunta era en términos de dosis absorbida. O sea, pues muchos fabricantes ponen en la propaganda del detector, dice, bueno, esto aguanta hasta 1000 Gray, 800 Gray, sí, o 500 RAM, o la dosis, o como quieran medir la dosis. Esa sería la pregunta.
I got you. So for that particular detector, 350 kV is what that's rated at. Our flat panel, 1611, is rated up to 15 MeV, and they told us 15 megagray of dose for the large detector. This one, I'm not sure. I haven't seen the data on that. I'm sorry. Yeah, I don't. This is so new that they haven't told me everything on that. But that's a really good question and something to think about. So we will have more information on that when it becomes available. So I'm sorry I couldn't answer that.
Buenos días. Mi pregunta va para el lado de la habilitación para utilizar ambos métodos, radiografía digital y radiografía directa, en la industria de oil and gas. Porque tengo entendido que hoy en día en Argentina no tenemos una habilitación directa para estos métodos, sino que sigue estando vigente la tradicional.
to. Who is the governing authority for inspections in Argentina? Is it ISO or AS?
Cuando hablamos de habilitaciones, hablamos de certificaciones, ¿no? Separemos eso porque justo acá estamos en el ámbito en el que necesitamos las habilitaciones también. Eso es importante saberlo. La nueva norma, esta que decía recién, ya contempla las técnicas de radiografía digital, así como también sumó las técnicas avanzadas de ultrasonido, entre otros métodos. Hoy en día se está trabajando con los niveles convencionales, es lo que hay, y hay algunos pocos niveles digitales que quedaron del 2018 cuando vinieron alemanes a certificar, ¿sí? Pero hoy en día se está trabajando con convencionales. Justo lo que decía al principio, la idea es poder avanzar hacia esos esquemas nuevos, ¿está bien? Donde también están todos invitados a colaborar y aportar, ¿no? Desde los comités técnicos asesores de los esquemas de certificación, pero la idea es avanzar eso. Hoy no hay niveles de digital, ¿sí? La norma plantea el nivel 1 de digital, el nivel 2, su correlación con los convencionales, ¿sí? Y hay algunos esquemas hasta que plantean los niveles 3, ¿sí? Que son superadores, ¿está? Bueno, esa es la... Hoy no hay niveles digitales, ¿sí? Al menos por IRAM NMISO 9712. Tenemos que elaborar para eso.
Buen día. La consulta es sobre el panel flexible, si admite algún grado de curvatura inversa a la que se puede utilizar.
Now, that's a great question. Currently, it can only bend this way around the panel, so it won't bend any further than that. The CR imaging plates, you could bend inversely. Oh, sorry. So yeah, you are limited with that to only one direction on the bend with the DDA. CR imaging plates, you could bend this way or that way. So if you have cylinders that you need to stick this into, the CR would be a better way to go than DDA. But that may be something in the future. These bendables are really new, so I'm sure there's going to be more and more need for something like that, that they will eventually come up with something. But now, no, just the one direction.
Realizamos dos preguntas más.
¿Ah? La pregunta es, ¿qué peso tiene ese panel flexible? ¿Cuánto pesa si yo lo quiero aplicar a una cañería de diámetro relativamente chico?
Okay. Actually, I can bring it to you. And this is supposed to be this is a demo panel, but this is the actual weight of what the real panel is going to be.
Alrededor de 1 kilo estaríamos.
What's that?
Okay.
Forgot my interpretation. 1 kilo, pretty light. Yeah,
More or less.
very light. And this is a prototype. They're going to make improvements on it too. We asked them to put rubber on here for better gripping on the pipe because it's a hard plastic and it slides. So they're going to improve that. Anybody else want to see? Yeah, pass. Yeah, you can pass it around the room.
Una última pregunta.
Muchas gracias, James.
Any-
Thank you.
Oh,
Antes de invitarlos a tomar
Thank
y
you.
compartir un rico café, les voy a pedir que todos se pongan de pie en sus asientos. A James le vamos a pedir que se ponga en la primera fila, se ubique en la primera fila. Así tomamos una foto de todos los participantes.
Miren a la cámara, por favor. Perfecto. En cámara.
Muchas gracias a todos. Los invitamos al foyer a compartir un coffee break y les pedimos, por favor, para mantener los horarios, que estemos de regreso puntualmente a las 11:30. Muchas gracias a todos.
I want you to get together. I want you to get together. I want you to get together. Put your hands together one time. I want you to get together. 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 want you to get together. I want you to get together. I want you to get together. Put your hands together one time. I want you to get together. I want you to get together.
La logística y el transporte de tu carga, esas por las que has trabajado con tanta dedicación, no pueden quedar en manos de cualquiera. Nuestro valor agregado, entender y anticiparnos a las necesidades logísticas de nuestros clientes. Entendemos que el transporte de carga es clave para las pequeñas, medianas empresas y los profesionales de la cadena de suministro. Sabemos que el ritmo de las industrias exige soluciones 24/7, donde lo digital se convierte en la vía más ágil y accesible. Y lo mejor de todo, sabemos que al elegir, la claridad en cada paso de la operación y en los costos es esencial para confiar en el mejor servicio. Abogamos por la simplicidad, la fiabilidad, la transparencia y la flexibilidad en un negocio que, aunque pueda parecer complejo, hemos transformado en algo fácil y accesible gracias a nuestros